The semiconductor in equilibrium. So far, we have been considering a general crystal and applying to it the concepts of quantum mechanics in order to determine a few of the characteristics of electrons in a single crystal lattice. In this chapter, we apply these concepts specifically to a semiconductor material. In particular, we use the density of quantum states in the conduction band and the density of quantum states in the valence band along with the Fermi-Dirac probability function to determine the concentration of electrons and holes in the conduction and valence bands, respectively. We also apply the concept of the Fermi energy to the semiconductor material. This chapter deals with the semiconductor in equilibrium. Equilibrium, or thermal equilibrium, implies that no external forces such as voltages, electric fields, magnetic fields, or temperature gradients are acting on the semiconductor. All properties of the semiconductor will be independent of time in this case. Preview. In this chapter, we will derive the thermal equilibrium concentrations of electrons and holes in a semiconductor as a function of the Fermi energy level. Discuss the process by which the properties of a semiconductor material can be favorably altered by adding specific impurity atoms to the semiconductor. Determine the thermal equilibrium concentrations of electrons and holes in a semiconductor as a function of the concentration of dopant atoms added to the semiconductor. Determine the position of the Fermi energy level as a function of the concentrations of dopant atoms added to the semiconductor. Charge carriers in semiconductors. Current is the rate at which charge flows. In a semiconductor, two types of charge carrier, the electron and the hole, can contribute to a current. Since the current in a semiconductor is determined largely by the number of electrons in the conduction band and the number of holes in the valence band, an important characteristic of the semiconductor is the density of these charge carriers. The density of electrons and holes is related to the density of states function and the Fermi distribution function, both of which we have considered. A qualitative discussion of these relationships will be followed by a more rigorous mathematical derivation of the thermal equilibrium concentration of electrons and holes. Equilibrium distribution of electrons and holes. The distribution, with respect to energy, of electrons in the conduction band is given by the density of allowed quantum states times the probability that a state is occupied by an electron. This statement is written in equation form as where E is the Fermi-Dirac probability function and E is the density of quantum states in the conduction band. The total electron concentration per unit volume in the conduction band is then found by integrating equation 4.1 over the entire conduction band energy. Similarly, the distribution, with respect to energy, of holes in the valence band is the density of allowed quantum states in the valence band multiplied by the probability that a state is not occupied by an electron. We may express this as the total hole concentration per unit volume is found by integrating this function over the entire valence band energy. To find the thermal equilibrium electron and hole concentrations, we need to determine the position of the Fermi energy F with respect to the bottom of the conduction band energy EC and the top of the valence band energy EV. To address this question, we will initially consider an intrinsic semiconductor. An ideal intrinsic semiconductor is a pure semiconductor with no impurity atoms and no lattice defects in the crystal, for example, pure silicon. We have argued in the previous chapter that, for an intrinsic semiconductor at T0K, all energy states in the valence band are filled with electrons and all energy states in the conduction band are empty of electrons. The Fermi energy must, therefore, be somewhere between EC and EV. The Fermi energy does not need to correspond to an allowed energy. As the temperature begins to increase above 0K, the valence electrons will gain thermal energy. A few electrons in the valence band may gain sufficient energy to jump to the conduction band. As an electron jumps from the valence band to the conduction band, an empty state, or hole, is created in the valence band. In an intrinsic semiconductor, then, electrons and holes are created in pairs by the thermal energy so that the number of electrons in the conduction band is equal to the number of holes in the valence band. Figure 4.1, a, density of states functions, Fermi-Dirac probability function, and areas representing electron and hole concentrations for the case when F is near the midgap energy, b, expanded view near the induction band energy, and c, expanded view near the valence band energy. Figure 4.1 shows a plot of the density of states function in the conduction band Gc, E, the density of states function in the valence band Gv, E, and the Fermi-Dirac probability function for t equals 0 k when F is approximately halfway between Ec and Ev. If we assume, for the moment, that the electron and hole effective masses are equal, then Gc, E, and Gv, E, are symmetrical functions about the midgap energy, the energy midway between Ec and Ev. We noted previously that the function ff, E, for E is greater than F is symmetrical to the function 1 minus ff, E, for E is less than F about the energy E equals F. This also means that the function ff, E, for E equals F plus D is equal to the function 1 minus F, E, for E equals F minus D. Figure 4.1b is an expanded view of the plot in Figure 4.1 as showing ff, E, and Gc, E, above the conduction band energy Ec. The product of Gc, E, and ff, E, is the distribution of electrons n, E, in the conduction band given by equation 4.1. This product is plotted in Figure 4.1a. Figure 4.1c, which is an expanded view of the plot in Figure 4.1a shows 1 minus f, E, and Gv, E, below the valence band energy eV. The product of Gv, E, and 1 minus f, E, is the distribution of holes p, E, in the valence band given by equation 4.2. This product is also plotted in Figure 4.1a. The areas under these curves are then the total density of electrons in the conduction band and the total density of holes in the valence band. From this we see that if Gc, E, and Gv, E, are symmetrical, the Fermi energy must be at the midgap energy in order to obtain equal electron and hole concentrations. If the effective masses of the electron and hole are not exactly equal, then the effective density of states functions Gc, E, and Gv, E, will not be exactly symmetrical about the midgap energy. The Fermi level for the intrinsic semiconductor will then shift slightly from the midgap energy in order to obtain equal electron and hole concentrations. The N0 and P0 equations. We have argued that the Fermi energy for an intrinsic semiconductor is near midgap. In deriving the equations for the thermal equilibrium concentration of electrons N0 and the thermal equilibrium concentration of holes P0, we will not be quite so restrictive. We will see later that, in particular situations, the Fermi energy can deviate from this midgap energy. We will assume initially, however, that the Fermi level remains within the bandgap energy. Thermal equilibrium electron concentration. The equation for the thermal equilibrium concentration of electrons may be found by integrating equation 4.1 over the conduction band energy, or the lower limit of integration is Ec and the upper limit of integration should be the top of the allowed conduction band energy. However, since the Fermi probability function rapidly approaches zero with increasing energy as indicated in Figure 4.1a, we can take the upper limit of integration to be infinity. We are assuming that the Fermi energy is within the forbidden energy band gap. For electrons in the conduction band, we have E greater than Ec. If Ec minus F is greater than caret, then E minus F is greater than caret, so that the Fermi probability function reduces to the Boltzmann approximation, one which is. Applying the Boltzmann approximation to equation 4.3, the thermal equilibrium density of electrons in the conduction band is found from. The integral of equation 4.5 may be solved more easily by making a change of variable. If we let, then equation 4.5 becomes. The integral is the gamma function, with a value of. Then equation 4.7 becomes. We may define a parameter nc as. The parameter mn** is the density of state's effective mass of the electron. The thermal equilibrium electron concentration in the conduction band can be written as: the parameter Nc is called the effective density of states function in the conduction band. If we were to assume that m*n m0, then the value of the effective density of states function at T equals 300 kelvins is Nc equals 25 quintillions per cubic centimeter, which is the order of magnitude of Nc for most semiconductors. If the effective mass of the electron is larger or smaller than m0, then the value of the effective density of states function changes accordingly, but is still of the same order of magnitude. Objective: calculate the probability that a quantum state in the conduction band at E equals EC plus caret divided by 2 is occupied by an electron, and calculate the thermal equilibrium electron concentration in silicon at T 300 K. Assume the Fermi energy is 0.25 electron volts below the conduction band. The value of Nc for silicon at temperature equals 300 kelvins is Nc equals 28 quintillions per cubic centimeter, see Appendix B. Solution: the probability that a quantum state at E equals EC plus caret divided by 2 is occupied by an electron is given by, or the electron concentration is given by, or comment. The probability of a state being occupied can be quite small, but the fact that there are a large number of states means that the electron concentration is a reasonable value. Thermal equilibrium hole concentration: the thermal equilibrium concentration of holes in the valence band is found by integrating equation 4.2 over the valence band energy, or we may note that for energy states in the valence band, E is less than eV. If F minus eV is greater than caret, the Fermi function is still assumed to be within the band gap, then we have a slightly different form of the Boltzmann approximation. Equation 413a may be written as: applying the Boltzmann approximation of equation 413b to equation 4.12, we find the thermal equilibrium concentration of holes in the valence band is, where the lower limit of integration is taken as -infinity instead of the bottom of the valence band. The exponential term decays fast enough so that this approximation is valid. Equation 4.14 may be solved more easily by again making a change of variable. If we let, then equation 4.14 becomes, where the negative sign comes from the differential d equals minus ktd. Note that the lower limit of becomes when if we change the order of integration, we introduce another minus sign. From equation 4.8, equation 4.16 becomes, we may define a parameter Nv as, which is called the effective density of states function in the valence band. The parameter Mp* is the density of states effective mass of the hole. The thermal equilibrium concentration of holes in the valence band may now be written as: the magnitude of Nv is also on the order of 10⁻19 per cubic centimeter at temperature 300 kelvins for most semiconductors. Objective: calculate the thermal equilibrium hole concentration in silicon at T 400 K. Assume that the Fermi energy is 0.27 electron volts above the valence band energy. The value of Nv for silicon at T equals 300 kelvins is Nv equals 10.4 quintillions per cubic centimeter. Solution: the parameter values at temperature 400 kelvins are found as, and the hole concentration is then, or comment. The parameter values at any temperature can easily be found by using the 300 K values and the temperature dependence. The effective density of states functions, Nc and Nv, are constant for a given semiconductor material at a fixed temperature. Table 4.1 gives the values of the density of states function and of the density of states effective masses for silicon, gallium arsenide, and germanium. Note that the value of Nc for gallium arsenide is smaller than the typical 10 quintillions per cubic centimeter value. This difference is due to the small electron effective mass in gallium arsenide. The thermal equilibrium concentrations of electrons in the conduction band and of holes in the valence band are directly related to the effective density of states constants and to the Fermi energy level. The intrinsic carrier concentration. For an intrinsic semiconductor, the concentration of electrons in the conduction band is equal to the concentration of holes in the valence band. We may denote Ni and pi as the electron and hole concentrations, respectively, in the intrinsic semiconductor. These parameters are usually referred to as the intrinsic electron concentration and intrinsic hole concentration. However, Ni pi, so normally we simply use the parameter Ni as the intrinsic carrier concentration, which refers to either the intrinsic electron or hole concentration. Table 4.1 Effective density of states function and density of states effective mass values. Silicon, gallium arsenide, germanium. The Fermi energy level for the intrinsic semiconductor is called the intrinsic Fermi energy, or F equals EFI. If we apply equations 4.11 and 4.19 to the intrinsic semiconductor, then we can write and. If we take the product of equations 4.20 and 4.21, we obtain or, where Eg is the band gap energy. For a given semiconductor material at a constant temperature, the value of Ni is a constant, and independent of the Fermi energy. The intrinsic carrier concentration for silicon at temperature equals 300 kelvins may be calculated by using the effective density of states function values from table 4.1. The value of Ni calculated from equation 4.23 for Eg equals 1.12 electron volts is Ni 6.95 billions per cubic centimeter. The commonly accepted value E2 of Ni for silicon at temperature equals 300 kelvins is approximately 15 billions per cubic centimeter. This discrepancy may arise from several sources. First, the values of the effective masses are determined at a low temperature where the cyclotron resonance experiments are performed. Since the effective mass is an experimentally determined parameter, and since the effective mass is a measure of how well a particle moves in a crystal, this parameter may be a slight function of temperature. Next, the density of states function for a semiconductor was obtained by generalizing the model of an electron in a three-dimensional infinite potential well. This theoretical function may also not agree exactly with experiment. However, the difference between the theoretical value and the experimental value of Ni is approximately a factor of 2, which, in many cases, is not significant. Table 4.2 lists the commonly accepted values of Ni for silicon, gallium arsenide, and germanium at temperature equals 300 kelvins. The intrinsic carrier concentration is a very strong function of temperature. Table 4.2 Commonly accepted values of Ni at temperature equals 300 kelvins. Silicon Ni equals 15 billions per cubic centimeter. Gallium arsenide Ni equals 1.8 millions per cubic centimeter. Germanium Ni 24 trillions per cubic centimeter. Objective: calculate the intrinsic carrier concentration in silicon at temperature 250 kelvins and at temperature 400 kelvins. The values of Nc and Nv for silicon at temperature 300 kelvins are 2.8 times 10 power 19 per cubic centimeter and 1.04 times 10 power 19 per cubic centimeter, respectively. Both Nc and Nv vary as temperature power 3/2. Assume the band gap energy of silicon is 1.12 electron volts and does not vary over this temperature range. Solution: using equation 4.23, we find, at temperature equals 250 kelvins. Or, at temperature equals 400 kelvins, we find. Or, comment. We may note from this example that the intrinsic carrier concentration increased by over 4 orders of magnitude as the temperature increased by 150 degrees Celsius. Figure 4.2 is a plot of Ni from equation 4.23, for silicon, gallium arsenide, and germanium as a function of temperature. As seen in the figure, the value of Ni for these semiconductors may easily vary over several orders of magnitude as the temperature changes over a reasonable range. Intrinsic carrier density. Figure 4.2. The intrinsic carrier concentration of germanium, silicon, and gallium arsenide as a function of temperature. The intrinsic Fermi level position. We have qualitatively argued that the Fermi energy level is located near the center of the forbidden band gap for the intrinsic semiconductor. We can specifically calculate the intrinsic Fermi level position. Since the electron and hole concentrations are equal, setting equations 4.20 and 4.21 equal to each other, we have. If we take the natural log of both sides of this equation and solve for EFI, we obtain. From the definitions for NC and NV given by equations 4.10 and 4.18, respectively, equation 4.25 may be written as the first term, 1/2 times conduction band energy plus valence band energy, is the energy exactly midway between conduction band energy and valence band energy, or the midgap energy. We can define so that if the electron and hole effective masses are equal so that hole mass equals electron mass, then the intrinsic Fermi level is exactly in the center of the band gap. If hole mass is greater than electron mass, the intrinsic Fermi level is slightly above the center, and if hole mass is smaller than electron mass, it is slightly below the center of the band gap. The density of states function is directly related to the carrier effective mass, thus, a larger effective mass means a larger density of states function. The intrinsic Fermi level must shift away from the band with the larger density of states in order to maintain equal numbers of electrons and holes. Objective: calculate the position of the intrinsic Fermi level with respect to the center of the band gap in silicon at temperature equals 300 kelvins. The density of states effective carrier masses in silicon are effective electron mass equals 1.08 normal electron mass and hole mass equals 0.56 normal electron mass. Solution: the intrinsic Fermi level with respect to the center of the band gap is. Or. Comment: the intrinsic Fermi level in silicon is 12.8 millielectron-volts below the midgap energy. If we compare 12.8 m electron-volts to 560 m electron-volts, which is 1/2 of the band gap energy of silicon, we can, in many applications, simply approximate the intrinsic Fermi level to be in the center of the band gap. Dopant atoms and energy levels. The intrinsic semiconductor may be an interesting material, but the real power of semiconductors is realized by adding small, controlled amounts of specific dopant, or impurity, atoms. This doping process, described briefly in Chapter 1, can greatly alter the electrical characteristics of the semiconductor. The doped semiconductor, called an extrinsic material, is the primary reason we can fabricate the various semiconductor devices that we will consider in later chapters. Qualitative description. In Chapter 3, we discussed the covalent bonding of silicon and considered the simple two-dimensional representation of the single crystal silicon lattice as shown in Figure 4.3. Now consider adding a group V element, such as phosphorus, as a substitutional impurity. The group V element has 5 valence electrons. 4 of these will contribute to the covalent bonding with the silicon atoms, leaving the 5th more loosely bound to the phosphorus atom. This effect is schematically shown in Figure 4.4. We refer to the 5th valence electron as a donor electron. The phosphorus atom without the donor electron is positively charged. At very low temperatures, the donor electron is bound to the phosphorus atom. However, by intuition, it should seem clear that the energy required to elevate the donor electron into the conduction band is considerably less than that for the electrons involved. In the covalent bonding, Figure 4.5 shows the energy band diagram that we would expect. The energy level, ED, is the energy state of the donor electron. Figure 4.3 two-dimensional representation of the intrinsic silicon lattice. Figure 4.4 two-dimensional representation of the silicon lattice doped with a phosphorus atom. Figure 4.5 The energy band diagram showing, a. the discrete donor energy state and, b. the effect of a donor state being ionized. If a small amount of energy, such as thermal energy, is added to the donor electron, it can be elevated into the conduction band, leaving behind a positively charged phosphorus ion. The electron in the conduction band can now move through the crystal generating a current, while the positively charged ion is fixed in the crystal. This type of impurity atom donates an electron to the conduction band and so is called a donor impurity atom. The donor impurity atoms add electrons to the conduction band without creating holes in the valence band. The resulting material is referred to as an N-type semiconductor, and for the negatively charged electron. Now consider adding a group 3 element, such as boron, as a substitutional impurity to silicon. The group 3 element has 3 valence electrons, which are all taken up in the covalent bonding. As shown in figure 4.6a, one covalent bonding position appears to be empty. If an electron were to occupy this empty position, its energy would have to be greater than that of the valence electrons, since the net charge state of the boron atom would now be negative. However, the electron occupying this empty position does not have sufficient energy to be in the conduction band, so its energy is far smaller than the conduction band energy. Figure 4.6b shows how valence electrons may gain a small amount of thermal energy and move about in the crystal. The empty position associated with the boron atom becomes occupied, and other valence electron positions become vacated. These other vacated electron positions can be thought of as holes in the semiconductor material. Figure 4.6 two-dimensional representation of a silicon lattice, A, doped with a boron atom and, B, showing the ionization of the boron atom resulting in a hole. Figure 4.7 the energy band diagram showing, A, the discrete acceptor energy state and, B, the effect of an acceptor state being ionized. Figure 4.7 shows the expected energy state of the empty position and also the formation of a hole in the valence band. The hole can move through the crystal generating a current, while the negatively charged boron atom is fixed in the crystal. The group 3 atom accepts an electron from the valence band and so is referred to as an acceptor impurity atom. The acceptor atom can generate holes in the valence band without generating electrons in the conduction band. This type of semiconductor material is referred to as a p-type material, P for the positively charged hole. The pure single crystal semiconductor material is called an intrinsic material. Adding controlled amounts of dopant atoms, either donors or acceptors, creates a material called an extrinsic semiconductor. An extrinsic semiconductor will have either a preponderance of electrons, N-type, or a preponderance of holes, p-type. Ionization energy. We can calculate the approximate distance of the donor electron from the donor impurity ion, and also the approximate energy required to elevate the donor electron into the conduction band. This energy is referred to as the ionization energy. We will use the Bohr model of the atom for these calculations. The justification for using this model is that the most probable distance of an electron from the nucleus in a hydrogen atom, determined from quantum mechanics, is the same as the Bohr radius. The energy levels in the hydrogen atom determined from quantum mechanics are also the same as obtained from the Bohr theory. In the case of the donor impurity atom, we may visualize the donor electron orbiting the donor ion, which is embedded in the semiconductor material. We will need to use the permittivity of the semiconductor material in the calculations rather than the permittivity of free space as is used in the case of the hydrogen atom. We will also use the effective mass of the electron in the calculations. The analysis begins by setting the Coulomb force of attraction between the electron and ion equal to the centripetal force of the orbiting electron. This condition will give a steady orbit. We have where v is the magnitude of the velocity and rn is the radius of the orbit. If we assume the angular momentum is also quantized, then we can write where n is a positive integer. Solving for v from equation 4.28, substituting into equation 4.27, and solving for the radius, we obtain The assumption of the angular momentum being quantized leads to the radius also being quantized. The Bohr radius is defined as. We can normalize the radius of the donor orbital to that of the Bohr radius, which gives. Where r is the relative dielectric constant of the semiconductor material, m0 is the rest mass of an electron, and m** is the conductivity effective mass of the electron in the semiconductor. If we consider the lowest energy state in which N1, and if we consider silicon in which relative dielectric constant equals 11.7 and the conductivity effective mass is 0.26 from normal electron mass, then we have that. Or R1 equals 23.9 angstroms. This radius corresponds to approximately 4 lattice constants of silicon. Recall that one unit cell in silicon effectively contains 8 atoms, so the radius of the orbiting donor electron encompasses many silicon atoms. The donor electron is not tightly bound to the donor atom. The total energy of the orbiting electron is given by where T is the kinetic energy and V is the potential energy of the electron. The kinetic energy is, using the velocity v from equation 4.28, and the radius Rn from equation 4.29, the kinetic energy becomes. The potential energy is. The total energy is the sum of the kinetic and potential energies, so that for the hydrogen atom, effective electron mass equals normal electron mass and dielectric constant equals dielectric constant of free space. The ionization energy of the hydrogen atom in the lowest energy state is then 3.6 electron volts. If we consider silicon, the ionization energy is 25.8 m electron volts, much less than the bandgap energy of silicon. This energy is the approximate ionization energy of the donor atom, or the energy required to elevate the donor electron into the conduction band. For ordinary donor impurities such as phosphorus or arsenic in silicon or germanium, this hydrogenic model works quite well and gives some indication of the magnitudes of the ionization energies involved. Table 4.3 lists the actual experimentally measured ionization energies for a few impurities in silicon and germanium. Germanium and silicon have different relative dielectric constants and effective masses. Thus, we expect the ionization energies to differ. Group 3-5 semiconductors. In the previous sections, we have discussed the donor and acceptor impurities in a group 4 semiconductor, such as silicon. The situation in the group 3-5 compound semiconductors, such as gallium arsenide, is more complicated. Group 2 elements, such as beryllium, zinc, and cadmium, can enter the lattice as substitutional impurities, replacing the group 3 gallium element to become acceptor impurities. Similarly, group 6 elements, such as selenium and tellurium, can enter the lattice substitutionally, replacing the group V arsenic element to become donor impurities. The corresponding ionization energies for these impurities are smaller than those for the impurities in silicon. The ionization energies for the donors in gallium arsenide are also smaller than those for the acceptors, because of the smaller effective mass of the electron compared to that of the hole. Table 4.3 Impurity ionization energies in silicon and germanium. Table 4.4 Impurity ionization energies in gallium arsenide. Group 4 elements, such as silicon and germanium, can also be impurity atoms in gallium arsenide. If a silicon atom replaces a gallium atom, the silicon impurity will act as a donor, but if the silicon atom replaces an arsenic atom, then the silicon impurity will act as an acceptor. The same is true for germanium as an impurity atom. Such impurities are called amphoteric. Experimentally in gallium arsenide, it is found that germanium is predominantly an acceptor and silicon is predominantly a donor. Table 4.4 lists the ionization energies for the various impurity atoms in gallium arsenide. The extrinsic semiconductor. We defined an intrinsic semiconductor as a material with no impurity atoms present in the crystal. An extrinsic semiconductor is defined as a semiconductor in which controlled amounts of specific dopant or impurity atoms have been added so that the thermal equilibrium electron and hole concentrations are different from the intrinsic carrier concentration. One type of carrier will predominate in an extrinsic semiconductor. Equilibrium distribution of electrons and holes. Adding donor or acceptor impurity atoms to a semiconductor will change the distribution of electrons and holes in the material. Since the Fermi energy is related to the distribution function, the Fermi energy will change as dopant atoms are added. Figure 4.8 Density of states functions, Fermi-Dirac probability function, and areas representing electron and hole concentrations for the case when F is above the intrinsic Fermi energy. If the Fermi energy changes from near the mid-gap value, the density of electrons in the conduction band and the density of holes in the valence band will change. These effects are shown in figures 4.8 and 4.9. Figure 4.8 shows the case for F is greater than EFI and figure 4.9 shows the case for F is less than EFI. When F is greater than EFI, the electron concentration is larger than the hole concentration, and when F is less than EFI, the hole concentration is larger than the electron concentration. When the density of electrons is greater than the density of holes, the semiconductor is N-type, donor impurity atoms have been added. When the density of holes is greater than the density of electrons, the semiconductor is P-type, acceptor impurity atoms have been added. The Fermi energy level in a semiconductor changes as the electron and hole concentrations change and, again, the Fermi energy changes as donor or acceptor impurities are added. The change in the Fermi level as a function of impurity concentrations is considered in section 4.6. Figure 4.9 Density of states functions, Fermi-Dirac probability function, and areas representing electron and hole concentrations for the case when F is below the intrinsic Fermi energy. The expressions previously derived for the thermal equilibrium concentration of electrons and holes, given by equations 4.11 and 4.19, are general equations for N0 and P0 in terms of the Fermi energy. These equations are again given as and. As we just discussed, the Fermi energy may vary through the band gap energy, which will then change the values of N0 and P0. Objective: calculate the thermal equilibrium concentrations of electrons and holes for a given Fermi energy. Consider silicon at temperature equals 300 Kelvin so that Nc equals 2.8 times 10 power 19 per cubic centimeter and Nv equals 1.04 times 10 power 19 per cubic centimeter. Assume that the Fermi energy is 0.25 electron volts below the conduction band. If we assume that the band gap energy of silicon is 1.12 electron volts, then the Fermi energy will be 0.87 electron volts above the valence band. Solution. Using equation 4.11, we have. From equation 4.19, we can write. Comment. The change in the Fermi level is actually a function of the donor or acceptor impurity concentrations that are added to the semiconductor. However, this example shows that electron and hole concentrations change by orders of magnitude from the intrinsic carrier concentration as the Fermi energy changes by a few tenths of an electron volt. In the previous example, since N0 is greater than P0, the semiconductor is N-type. In an N-type semiconductor, electrons are referred to as the majority carrier and holes as the minority carrier. By comparing the relative values of N0 and P0 in the example, it is easy to see how this designation came about. Similarly, in a P-type semiconductor where P0 is greater than N0, holes are the majority carrier and electrons are the minority carrier. We may derive another form of the equations for the thermal equilibrium concentrations of electrons and holes. If we add and subtract an intrinsic Fermi energy in the exponent of equation 4.11, we can write. Or, the intrinsic carrier concentration is given by equation 4.20 as. So that the thermal equilibrium electron concentration can be written as. Similarly, if we add and subtract an intrinsic Fermi energy in the exponent of equation 4.19, we will obtain. As we will see, the Fermi level changes when donors and acceptors are added, but equations 4.39, and 4.40, show that, as the Fermi level changes from the intrinsic Fermi level, N0 and P0 change from the Ni value. If F is greater than EFI, then we will have N0 greater than Ni and P0 less than Ni. One characteristic of an N-type semiconductor is that F is greater than EFI so that N0 is greater than P0. Similarly, in a P-type semiconductor, F is less than EFI so that P0 is greater than Ni and N0 is less than Ni, thus, P0 is greater than N0. We can see the functional dependence of N0 and P0 with F in figures 4.8 and 4.9. As F moves above or below EFI, the overlapping probability function with the density of states functions in the conduction band and valence band changes. As F moves above EFI, the probability function in the conduction band increases, while the probability, 1 minus FF, E, of an empty state, hole, in the valence band decreases. As F moves below EFI, the opposite occurs. The N0-P0 product. We may take the product of the general expressions for N0 and P0 as given in equations 4.11 and 4.19, respectively. The result is, which may be written as equation 4.42 was derived for a general value of Fermi energy. The values of N0 and P0 are not necessarily equal. However, equation 4.42 is exactly the same as equation 4.23, which we derived for the case of an intrinsic semiconductor. We then have that, for the semiconductor in thermal equilibrium, equation 4.43 states that the product of N0 and P0 is always a constant for a given semiconductor material at a given temperature. Although this equation seems very simple, it is one of the fundamental principles of semiconductors in thermal equilibrium. The significance of this relation will become more apparent in the chapters that follow. It is important to keep in mind that equation 4.43 was derived using the Boltzmann approximation. If the Boltzmann approximation is not valid, then likewise, equation 4.43 is not valid. An extrinsic semiconductor in thermal equilibrium does not, strictly speaking, contain an intrinsic carrier concentration, although some thermally generated carriers are present. The intrinsic electron and hole carrier concentrations are modified by the donor or acceptor impurities. However, we may think of the intrinsic concentration Ni in equation 4.43 simply as a parameter of the semiconductor material. The Fermi-Dirac integral. In the derivation of the equations 4.11 and 4.19 for the thermal equilibrium electron and hole concentrations, we assumed that the Boltzmann approximation was valid. If the Boltzmann approximation does not hold, the thermal equilibrium electron concentration is written from equation 4.3 as. If we again make a change of variable and let and also define, then we can rewrite equation 4.44 as. The integral is defined as. This function, called the Fermi-Dirac integral, is a tabulated function of the variable NIF. Figure 4.10 is a plot of the Fermi-Dirac integral. Note that if NIF is greater than 0, then F is greater than EC, thus, the Fermi energy is actually in the conduction band. Objective: calculate the electron concentration using the Fermi-Dirac integral. Let NIF2 so that the Fermi energy is above the conduction band by approximately 52 m electron volts at temperature 300 kelvins. Solution. Equation 4.46 can be written as: for silicon at temperature equals 300 kelvins, Nc equals 2.8 times 10 power 19 per cubic centimeter, and, from figure 4.10, the Fermi-Dirac integral has a value or F1 equals 2.7. Then. Comment. Note that if we had used equation 4.11, the thermal equilibrium value of N0 would be N0 equals 2.08 times 10 power 20 per cubic centimeter, which is incorrect since the Boltzmann approximation is not valid for this. case. We may use the same general method to calculate the thermal equilibrium concentration of holes. We obtain Figure 4.10 the Fermi-Dirac integral F1/2 as a function of the Fermi energy, where and the integral in equation 4.48 is the same Fermi-Dirac integral defined by equation 4.47, although the variables have slightly different definitions. We may note that if Ni is greater than 0, then the Fermi level is in the valence band. Degenerate and non-degenerate semiconductors. In our discussion of adding dopant atoms to a semiconductor, we have implicitly assumed that the concentration of dopant atoms added is small when compared to the density of host or semiconductor atoms. The small number of impurity atoms are spread far enough apart so that there is no interaction between donor electrons, for example, in an N-type material. We have assumed that the impurities introduce discrete, non-interacting donor energy states in the N-type semiconductor and discrete, non-interacting acceptor states in the P-type semiconductor. These types of semiconductors are referred to as non-degenerate semiconductors. If the impurity concentration increases, the distance between the impurity atoms decreases and a point will be reached when donor electrons, for example, will begin to interact with each other. When this occurs, the single discrete donor energy will split into a band of energies. As the donor concentration further increases, the band of donor states widens and may overlap the bottom of the conduction band. This overlap occurs when the donor concentration becomes comparable with the effective density of states. When the concentration of electrons in the conduction band exceeds the density of states Nc, the Fermi energy lies within the conduction band. This type of semiconductor is called a degenerate N-type semiconductor. In a similar way, as the acceptor doping concentration increases in a P-type semiconductor, the discrete acceptor energy states will split into a band of energies and may overlap the top of the valence band. The Fermi energy will lie in the valence band when the concentration of holes exceeds the density of states Nv. This type of semiconductor is called a degenerate P-type semiconductor. Schematic models of the energy band diagrams for a degenerate N-type and degenerate P-type semiconductor are shown in figure 4.11. The energy states below F are mostly filled with electrons and the energy states above F are mostly empty. In the degenerate N-type semiconductor, the states between F and EC are mostly filled with electrons, thus, the electron concentration in the conduction band is very large. Similarly, in the degenerate P-type semiconductor, the energy states between F and F are mostly empty, thus, the hole concentration in the valence band is very large. Figure 4.11 simplified energy band diagrams for degenerately doped, A, N-type and, B, P-type semiconductors. Statistics of donors and acceptors. In the previous chapter, we discussed the Fermi-Dirac distribution function, which gives the probability that a particular energy state will be occupied by an electron. We need to reconsider this function and apply the probability statistics to the donor and acceptor energy states. Probability function. One postulate used in the derivation of the Fermi-Dirac probability function was the Pauli exclusion principle, which states that only one particle is permitted in each quantum state. The Pauli exclusion principle also applies to the donor and acceptor states. Suppose we have Ni electrons and Gi quantum states, where the subscript I indicates the ith energy level. There are Gi ways of choosing where to put the first particle. Each donor level has two possible spin orientations for the donor electron, thus, each donor level has two quantum states. The insertion of an electron into one quantum state, however, precludes putting an electron into the second quantum state. By adding one electron, the vacancy requirement of the atom is satisfied, and the addition of a second electron in the donor level is not possible. The distribution function of donor electrons in the donor energy states is then slightly different than the Fermi-Dirac function. The probability function of electrons occupying the donor state is where North Dakota is the density of electrons occupying the donor level and ED is the energy of the donor level. The factor 1/2 in this equation is a direct result of the spin factor just mentioned. The 1/2 factor is sometimes written as 1 divided by g, where g is called a degeneracy factor. Equation 4.50 can also be written in the form where North Dakota is the concentration of ionized donors. In many applications, we will be interested more in the concentration of ionized donors than in the concentration of electrons remaining in the donor states. If we do the same type of analysis for acceptor atoms, we obtain the expression where Na is the concentration of acceptor atoms, Ea is the acceptor energy level, Pa is the concentration of holes in the acceptor states, and Na-S the concentration of ionized acceptors. A hole in an acceptor state corresponds to an acceptor atom that is neutrally charged and still has an empty bonding position, as we have discussed in section 4.2.1. The parameter G is, again, a degeneracy factor. The ground state degeneracy factor G is normally taken as 4 for the acceptor level in silicon and gallium arsenide because of the detailed band structure. Complete ionization and freeze out. The probability function for electrons in the donor energy state was just given by equation 4.50. If we assume that ed-f is much greater than caret, then if ed-f is much greater than caret, then the Boltzmann approximation is also valid for the electrons in the conduction band, so that, from equation 4.11, we can determine the relative number of electrons in the donor state compared with the total number of electrons. Therefore, we can consider the ratio of electrons in the donor state to the total number of electrons in the conduction band plus donor state. Using the expressions of equations 4.53 and 4.11, we write the Fermi energy cancels out of this expression. Dividing by the numerator term, we obtain the factor, Ec minus ed, is just the ionization energy of the donor electrons. Objective, determine the fraction of total electrons still in the donor states at temperature equals 300 kelvins. Consider phosphorus doping in silicon, for temperature equals 300 kelvins, at a concentration of North Dakota equals 10 power 16 per cubic centimeter. Solution. Using equation 4.55, we find. Comment. This example shows that there are very few electrons in the donor state compared with the conduction band. Essentially all of the electrons from the donor states are in the conduction band, and, since only about 0.4% of the donor states contain electrons, the donor states are said to be completely ionized. At room temperature, then, the donor states are essentially completely ionized, and, for a typical doping of 10 power 16 per cubic centimeter, almost all donor impurity atoms have donated an electron to the conduction band. At room temperature, there is also essentially complete ionization of the acceptor atoms. This means that each acceptor atom has accepted an electron from the valence band, so that Pa is 0. At typical acceptor doping concentrations, a hole is created in the valence band for each acceptor atom. This ionization effect and the creation of electrons and holes in the conduction band and valence band, respectively, are shown in figure 4.12. The opposite of complete ionization occurs at temperature equals 0 kelvins. At absolute 0 degrees, all electrons are in their lowest possible energy state, that is, for an N-type semiconductor, each donor state must contain an electron, therefore North Dakota or North Dakota 0. We must have, then, from equation 4.50, that exponential, ed minus f, divided by kT0. Since temperature equals 0 K, this will occur for exponential minus infinity. Which means that f is greater than addition. The Fermi energy level must be above the donor energy level at absolute 0. In the case of a p-type semiconductor at absolute 0 temperature, the impurity atoms will not contain any electrons, so that the Fermi energy level must be below the acceptor energy state. The distribution of electrons among the various energy states, and hence the Fermi energy, is a function of temperature. Figure 4.12 energy band diagrams showing complete ionization of A. Donor states and B. Acceptor states. Figure 4.13 energy band diagram at temperature 0 kelvins for A. N-type and B. P-type semiconductors. A detailed analysis, not given in this text, shows that at temperature equals 0 kelvins, the Fermi energy is halfway between EC and ED for the N-type material and halfway between EA and EV for the P-type material. Figure 4.13 shows these effects. No electrons from the donor state are thermally elevated into the conduction band. This effect is called freeze-out. Similarly, when no electrons from the valence band are elevated into the acceptor states, the effect is also called freeze-out. Between temperature equals 0 kelvins, freeze-out, and temperature equals 300 kelvins, complete ionization, we have partial ionization of donor or acceptor atoms. Objective: determine the temperature at which 90% of acceptor atoms are ionized. Consider p-type silicon doped with boron at a concentration of Na10^16 per cubic centimeter. Solution: find the ratio of holes in the acceptor state to the total number of holes in the valence band plus acceptor state. Taking into account the Boltzmann approximation and assuming the degeneracy factor is 4, we write for 90% ionization. Using trial and error, we find that temperature equals 193 kelvins. Comment: this example shows that at approximately 100 C below room temperature, we still have 90% of the acceptor atoms ionized. In other words, 90% of the acceptor atoms have donated a hole to the valence band. Charge neutrality. In thermal equilibrium, the semiconductor crystal is electrically neutral. The electrons are distributed among the various energy states, creating negative and positive charges, but the net charge density is 0. This charge neutrality condition is used to determine the thermal equilibrium electron and hole concentrations as a function of the impurity doping concentration. We will define a compensated semiconductor and then determine the electron and hole concentrations as a function of the donor and acceptor concentrations. Compensated semiconductors. A compensated semiconductor is one that contains both donor and acceptor impurity atoms in the same region. A compensated semiconductor can be formed, for example, by diffusing acceptor impurities into an N-type material or by diffusing donor impurities into a P-type material. An N-type compensated semiconductor occurs when North Dakota is greater than Na, and a P-type compensated semiconductor occurs when Na is greater than North Dakota. If Na North Dakota, we have a completely compensated semiconductor that has, as we will show, the characteristics of an intrinsic material. Compensated semiconductors are created quite naturally during device fabrication, as we will see later. Figure 4.14 energy band diagram of a compensated semiconductor showing ionized and unionized donors and acceptors. Equilibrium electron and hole concentrations. Figure 4.14 shows the energy band diagram of a semiconductor when both donor and acceptor impurity atoms are added to the same region to form a compensated semiconductor. The figure shows how the electrons and holes can be distributed among the various states. The charge neutrality condition is expressed by equating the density of negative charges to the density of positive charges. We then have or where N0 and P0 are the thermal equilibrium concentrations of electrons and holes in the conduction band and valence band, respectively. The parameter North Dakota is the concentration of electrons in the donor energy states, so ND equals North Dakota minus North Dakota is the concentration of positively charged donor states. Similarly, Pa is the concentration of holes in the acceptor states, so Na equals Na minus Pa is the concentration of negatively charged acceptor states. We have expressions for N0, P0, North Dakota, and Pa in terms of the Fermi energy and temperature. Thermal equilibrium electron concentration. If we assume complete ionization, North Dakota and Pa are both 0, and equation 4.57 becomes: if we express P0 as Ni squared divided by N0, then equation 4.58 can be written as, which in turn can be written as, the electron concentration N0 can be determined using the quadratic formula, or the positive sign in the quadratic formula must be used, since, in the limit of an intrinsic semiconductor when Na equals North Dakota equals 0, the electron concentration must be a positive quantity, or N0 equals Ni. Equation 4.60 is used to calculate the electron concentration in an N-type semiconductor, or when North Dakota is greater than Na. Although equation 4.60 was derived for a compensated semiconductor, the equation is also valid for Na equals 0. Objective: determine the thermal equilibrium electron and hole concentrations in silicon at temperature equals 300 kelvins for given doping concentrations. A. Let North Dakota equals 10 power 16 per cubic centimeter and Na equals 0. B. Let North Dakota equals 5 times 10 power 15 per cubic centimeter and Na equals 2 times 10 power 15 per cubic centimeter. Recall that Ni equals 1.5 times 10 power 10 per cubic centimeter in silicon at temperature equals 300 kelvins. Solution. A. From equation 4.60, the majority carrier electron concentration is. The minority carrier hole concentration is found to be. Again, from equation 4.60, the majority carrier electron concentration is. The minority carrier hole concentration is. Comment. In both parts of this example, North Dakota minus Na is much greater than Ni, so the thermal equilibrium majority carrier electron concentration is essentially equal to the difference between the donor and acceptor concentrations. Also, in both cases, the majority carrier electron concentration is orders of magnitude larger than the minority carrier hole concentration. We have argued in our discussion, and we may note from the results of example 4.9 that the concentration of electrons in the conduction band increases above the intrinsic carrier concentration as we add donor impurity atoms. At the same time, the minority carrier hole concentration decreases below the intrinsic carrier concentration as we add donor atoms. We must keep in mind that as we add donor impurity atoms and the corresponding donor electrons, there is a redistribution of electrons among available energy states. Figure 4.15 shows a schematic of this physical redistribution. A few of the donor electrons will fall into the empty states in the valence band and, in doing so, will annihilate some of the intrinsic holes. The minority carrier hole concentration will therefore decrease as we have seen in example 4.9. At the same time, because of this redistribution, the net electron concentration in the conduction band is not simply equal to the donor concentration plus the intrinsic electron concentration. Figure 4.15 energy band diagram showing the redistribution of electrons when donors are added. Objective: calculate the thermal equilibrium electron and hole concentrations in germanium for a given doping concentration. Consider a germanium sample at temperature equals 300 kelvins in which North Dakota equals 2 times 10 power 14 per cubic centimeter and Na equals 0. Assume that Ni equals 2.4 times 10 power 13 per cubic centimeter. Solution. Again, from equation 4.60, the majority carrier electron concentration is. The minority carrier hole concentration is. Comment. If the donor impurity concentration is not too different in magnitude from the intrinsic carrier concentration, then the thermal equilibrium majority carrier electron concentration is influenced by the intrinsic concentration. We have seen that the intrinsic carrier concentration Ni is a very strong function of temperature. As the temperature increases, additional electron-hole pairs are thermally generated so that the Ni squared term in equation 4.60 may begin to dominate. The semiconductor will eventually lose its extrinsic characteristics. Figure 4.16 shows the electron concentration versus temperature in silicon doped with 5 times 10 power 14 donors per cubic centimeter. As the temperature increases, we can see where the intrinsic concentration begins to dominate. Also shown is the partial ionization, or the onset of freeze-out, at the low temperature. Thermal equilibrium hole concentration. If we reconsider equation 4.58, and express N0 as Ni squared divided by P0, then we have, which we can write as Figure 4.16 electron concentration versus temperature, showing the three regions, partial ionization, extrinsic, and intrinsic. Using the quadratic formula, the hole concentration is given by, where the positive sign, again, must be used. Equation 4.62 is used to calculate the thermal equilibrium majority carrier hole concentration in a p-type semiconductor, or when Na is greater than North Dakota. This equation also applies for North Dakota equals 0. Objective: calculate the thermal equilibrium electron and hole concentrations in a compensated p-type semiconductor. Consider a silicon semiconductor at temperature equals 300 kelvins in which Na equals 10 power 16 per cubic centimeter and North Dakota equals 3 times 10 power 15 per cubic centimeter. Assume Ni equals 1.5 times 10 power 10 per cubic centimeter. Solution: since Na is greater than North Dakota, the compensated semiconductor is p-type and the thermal equilibrium majority carrier hole concentration is given by equation 4.62, as so that the minority carrier electron concentration is. Comment: if we assume complete ionization and if Na minus North Dakota is much greater than Ni, then the majority carrier hole concentration is, to a very good approximation, just the difference between the acceptor and donor concentrations. We may note that, for a compensated p-type semiconductor, the minority carrier electron concentration is determined from equations 4.60 and 4.62 are used to calculate the majority carrier electron concentration in an N-type semiconductor and majority carrier hole concentration in a p-type semiconductor, respectively. The minority carrier hole concentration in an N-type semiconductor could, theoretically, be calculated from equation 4.62. However, we would be subtracting two numbers on the order of 10 power 16 per cubic centimeter, for example, to obtain a number on the order of 10,000 per cubic centimeter, which from a practical point of view is not possible. The minority carrier concentrations are calculated from N0 P0 Ni2 once the majority carrier concentration has been determined. Position of Fermi energy level. We have discussed qualitatively in section 4.3.1 how the electron and hole concentrations change as the Fermi energy level moves through the bandgap energy. Then, in section 4.5, we calculated the electron and hole concentrations as a function of donor and acceptor impurity concentrations. We can now determine the position of the Fermi energy level as a function of the doping concentrations and as a function of temperature. The relevance of the Fermi energy level will be further discussed after the mathematical derivations. Mathematical derivation. The position of the Fermi energy level within the bandgap can be determined by using the equations already developed for the thermal equilibrium electron and hole concentrations. If we assume the Boltzmann approximation to be valid, then from equation 4.11, we have N0 equals Nc exponential minus Ec minus f divided by carrot. We can solve for Ec minus f from this equation and obtain, where N0 is given by equation 4.60. If we consider an N-type semiconductor in which North Dakota is much greater than Ni, then N0 equals North Dakota, so that the distance between the bottom of the conduction band and the Fermi energy is a logarithmic function of the donor concentration. As the donor concentration increases, the Fermi level moves closer to the conduction band. Conversely, if the Fermi level moves closer to the conduction band, then the electron concentration in the conduction band is increasing. We may note that if we have a compensated semiconductor, then the North Dakota term in equation 4.64 is simply replaced by North Dakota minus Na, or the net effective donor concentration. Objective: determine the required donor impurity concentration to obtain a specified Fermi energy. Silicon at temperature equals 300 kelvins contains an acceptor impurity concentration of Na equals 10 power 16 per cubic centimeter. Determine the concentration of donor impurity atoms that must be added so that the silicon is N-type and the Fermi energy is 0.20 electron volts below the conduction band H. Solution. From equation 4.64, we have, which can be rewritten as then, or. Comment. A compensated semiconductor can be fabricated to provide a specific Fermi energy level. We may develop a slightly different expression for the position of the Fermi level. We had from equation 4.39 that N0 equals Ni exponential F minus EFI divided by caret. We can solve for F minus EFI as equation 4.65 can be used specifically for an N-type semiconductor, where N0 is given by equation 4.60, to find the difference between the Fermi level and the intrinsic Fermi level as a function of the donor concentration. We may note that, if the net effective donor concentration is 0, that is, North Dakota minus Na equals 0, then N0 equals Ni and F equals EFI. A completely compensated semiconductor has the characteristics of an intrinsic material in terms of carrier concentration and Fermi level position. We can derive the same types of equations for a p-type semiconductor. From equation 4.19, we have P0 equals NV exponential F minus EV divided by KT, so that if we assume that Na is much greater than Ni, then equation 4.66 can be written as the distance between the Fermi level and the top of the valence band energy for a p-type semiconductor is a logarithmic function of the acceptor concentration. As the acceptor concentration increases, the Fermi level moves closer to the valence band. Equation 4.67 still assumes that the Boltzmann approximation is valid. Again, if we have a compensated p-type semiconductor, then the Na term in equation 4.67 is replaced by Na minus North Dakota, or the net effective acceptor concentration. We can also derive an expression for the relationship between the Fermi level and the intrinsic Fermi level in terms of the hole concentration. We have from equation 4.40 that P0 equals Ni exponential F minus EFI divided by caret, which yields equation 4.68 can be used to find the difference between the intrinsic Fermi level and the Fermi energy in terms of the acceptor concentration. The hole concentration P0 in equation 4.68 is given by equation 4.62. Figure 4.17 position of Fermi level for an A, N-type, North Dakota is greater than Na, and B, P-type, North Dakota is greater than Na, semiconductor. We may again note from equation 4.65 that, for an N-type semiconductor, N0 is greater than Ni and F is greater than EFI. The Fermi level for an N-type semiconductor is above EFI. For a p-type semiconductor, P0 is greater than Ni, and from equation 4.68, we see that EFI is greater than F. The Fermi level for a p-type semiconductor is below EFI. These results are shown in figure 4.17. Variation of F with doping concentration and temperature. We may plot the position of the Fermi energy level as a function of the doping concentration. Figure 4.18 shows the Fermi energy level as a function of donor concentration, N-type, and as a function of acceptor concentration, P-type, for silicon at temperature equals 300 kelvins. As the doping levels increase, the Fermi energy level moves closer to the conduction band for the N-type material and closer to the valence band for the P-type material. Keep in mind that the equations for the Fermi energy level that we have derived assume that the Boltzmann approximation is valid. Figure 4.18 position of Fermi level as a function of donor concentration, N-type, and acceptor concentration, P-type. Objective, determine the Fermi energy level and the maximum doping concentration at which the Boltzmann approximation is still valid. Consider p-type silicon, at temperature equals 300 kelvins, doped with boron. We may assume that the limit of the Boltzmann approximation occurs when F-Ea equals 3 kT. See section 4.1.2. Solution. From table 4.3, we find the ionization energy is Ea minus Ev equals 0.045 electron volts for boron in silicon. If we assume that EFI emit gap, then from equation 4.68, the position of the Fermi level at the maximum doping is given by or. We can then solve for the doping as comment. If the acceptor, or donor, concentration in silicon is greater than approximately 3 times 10 power 17 per cubic centimeter, then the Boltzmann approximation of the distribution function becomes less valid and the equations for the Fermi level position are no longer quite as accurate. The intrinsic carrier concentration Ni, in equations 4.65 and 4.68, is a strong function of temperature, so that F is a function of temperature also. Figure 4.19 shows the variation of the Fermi energy level in silicon with temperature for several donor and acceptor concentrations. As the temperature increases, Ni increases, and F moves closer to the intrinsic Fermi level. At high temperature, the semiconductor material begins to lose its extrinsic characteristics and begins to behave more like an intrinsic semiconductor. At the very low temperature, freeze-out occurs, the Boltzmann approximation is no longer valid and the equations we derived for the Fermi level position no longer apply. At the low temperature where freeze-out occurs, the Fermi level goes above Ed for the N-type material and below Ea for the P-type material. At absolute 0 degrees, all energy states below F are full and all energy states above F are empty. Relevance of the Fermi energy. We have been calculating the position of the Fermi energy level as a function of doping concentrations and temperature. This analysis may seem somewhat arbitrary and fictitious. However, these relations do become significant later in our discussion of p-n junctions and the other semiconductor devices we consider. An important point is that, in thermal equilibrium, the Fermi energy level is a constant throughout a system. We will not prove this statement, but we can intuitively see its validity by considering the following example. Figure 4.19 position of Fermi level as a function of temperature for various doping concentrations. Suppose we have a particular material, A, whose electrons are distributed in the energy states of an allowed band as shown in figure 420A. Most of the energy states below EFA contain electrons and most of the energy states above EFA are empty of electrons. Consider another material, B, whose electrons are distributed in the energy states of an allowed band as shown in figure 420B. The energy states below EFB are mostly full and the energy states above EFB are mostly empty. If these two materials are brought into intimate contact, the electrons in the entire system will tend to seek the lowest possible energy. Electrons from material A will flow into the lower energy states of material B, as indicated in figure 420C, until thermal equilibrium is reached. Thermal equilibrium occurs when the distribution of electrons, as a function of energy, is the same in the two materials. This equilibrium state occurs when the Fermi energy is the same in the two materials as shown in figure 420D. The Fermi energy, important in the physics of the semiconductor, also provides a good pictorial representation of the characteristics of the semiconductor materials and devices. Figure 4.20 The Fermi energy of A, material A in thermal equilibrium, B, material B in thermal equilibrium, C, materials A and B at the instant they are placed in contact, and D, materials A and B in contact at thermal equilibrium. Summary. The concentration of electrons in the conduction band is the integral over the conduction band energy of the product of the density of states function in the conduction band and the Fermi-Dirac probability function. The concentration of holes in the valence band is the integral over the valence band energy of the product of the density of states function in the valence band and the probability of a state being empty, which is 1 minus f, e. Using the Maxwell-Boltzmann approximation, the thermal equilibrium concentration of electrons in the conduction band is given by where Nc is the effective density of states in the conduction band. Using the Maxwell-Boltzmann approximation, the thermal equilibrium concentration of holes in the valence band is given by where Nv is the effective density of states in the valence band. The intrinsic carrier concentration is found from the concept of doping the semiconductor with donor, group V elements, impurities and acceptor, group 3 elements, impurities to form N-type and P-type extrinsic semiconductors was discussed. The fundamental relationship of N0P0Ni2 was derived. Using the concepts of complete ionization and charge neutrality, equations for the electron and hole concentrations as a function of impurity doping concentrations were derived. The position of the Fermi energy level as a function of impurity doping concentrations was derived. The relevance of the Fermi energy was discussed. The Fermi energy is a constant throughout a semiconductor that is in thermal equilibrium. Glossary of important terms. Acceptor atoms, impurity atoms added to a semiconductor to create a p-type material. Charge carrier, the electron and slash or hole that moves inside the semiconductor and gives rise to electrical currents. Compensated semiconductor, a semiconductor that contains both donors and acceptors in the same semiconductor region. Complete ionization, the condition when all donor atoms are positively charged by giving up their donor electrons and all acceptor atoms are negatively charged by accepting electrons. Degenerate semiconductor, a semiconductor whose electron concentration or hole concentration is greater than the effective density of states, so that the Fermi level is in the conduction band, N-type, or in the valence band, P-type. Donor atoms, impurity atoms added to a semiconductor to create an N-type material. Effective density of states, the parameter Nc, which results from integrating the density of quantum states Gc, E, times the Fermi function ff, E, over the conduction band energy, and the parameter Nv, which results from integrating the density of quantum states Gv, E, times 1 minus f, E, over the valence band energy. Extrinsic semiconductor, a semiconductor in which controlled amounts of donors and slash or acceptors have been added so that the electron and hole concentrations change from the intrinsic carrier concentration and a preponderance of either electrons, N-type, or holes, P-type, is created. Freeze out, the condition that occurs in a semiconductor when the temperature is lowered and the donors and acceptors become neutrally charged. The electron and hole concentrations become very small.